So I'm going to begin then by introducing Dr. Ciaran Beggan from the British Geological Survey, and his title is From Raspberries to Auroras, Building a School's Magnetometer Network in the UK. Ciaran.
I'll give you 5 minutes. Okay, good afternoon. Thank you everybody for coming, and thank you to the Auroras for the kind invitation to talk about one of the kind of outreach projects that I've been doing for the past few years. So it's entitled From Raspberries to Aurora, and hopefully by the time you get to the end you'll understand why it's got that title. First of all, I suppose what you'd be interested in understanding. Oops, it's not working. We got the clicker. So first of all, from that title, I've used the word magnetometers, and you might be wondering what a magnetometer is, and it's really just a very sensitive compass. So hopefully at some point, is that working? Sorry. So hopefully at some point you'll use a compass like this, and as you know, a compass detects the sort of direction towards magnetic north. That's a sort of standard compass you go out and have a look at when using a map in the hills and so on. You might be more familiar with these kind of compasses, which are the kind you'd have on a boat, for example. This is a sort of compass that Columbus might have used to cross the Atlantic. Nowadays on aircraft you get compasses, gyros and stuff like that. This is a picture from a Harrier jump jet, actually, built in the 70s. So as you can see, they weren't really built for luxury for the pilot, but the compass is there in the corner, and you probably all have one of these compasses in your phone, or in your pockets nowadays in terms of a phone. So these are all the different kind of compasses you get that are used for, say, sort of navigation or kind of commercial consumer purposes. Where does the magnetic field come from that your compass is sensing and detecting? Well, most of it comes from the outer core of the Earth. The outer core here is this sort of large circle. It's about the size of Mars, and the smaller circle in the middle is the inner core, which is solid. But the liquid outer core generates the main magnetic field through basically converting motion into electrical and then magnetic field energy, which then sort of escapes the core and forms a sort of general dipole magnetic field. At this point on the surface of the Earth, you're around about 3,500 kilometers away from it, so it's pretty weak. And in fact, it's weaker than your average fridge magnet, as you might know. If you put a magnet against a compass, it'll quickly deflect it. And the thing about that field is it changes very slowly over time. I'm talking years to millennia, so it's not a particularly rapidly changing field. The other main source of the magnetic field that your compass will detect is from the external magnetic field, and that's due to the currents, the electrical currents that flow in the upper atmosphere and sort of the near-Earth space. That's mainly driven by the interaction of the sun's magnetic field with the Earth's magnetic field, and because it's a lot nearer to you, it's only about 100 or a few hundred kilometers away, although it's not as strong in terms of the size of the currents that are being generated in the ionosphere. Because it's closer, it does generate a perceptible magnetic field that you can measure. And it changes very rapidly, typically over seconds when you're looking at geomagnetic storms caused by the sun, to sort of days when the Earth's magnetic field is recovering from a geomagnetic storm. And the external field to internal field ratio is about 1 to 100. So the main magnetic field caused by the core is about 100 times stronger than the external field. So very, very weak. So what has that got to do with a Raspberry Pi magnetometer, as I started the talk with? Well, what we're really interested in is the variation of the Earth's external field, and that's one of my research areas, looking at how the Earth's technology systems react when you get large-scale aurora and large-scale geomagnetic storms in the sky. So a couple of years ago, I had this idea about trying to detect the aurora with a school's magnetometer, and something that was sort of cheap and cheerful, and that could be used to sort of show you when the magnetic field was being disturbed by electrical currents in the sky, which are what generate the aurora. So there's a nice picture here of the aurora on the west coast of Scotland, and you can see it here. This is somewhere near Greenock, near Glasgow, and you can see some nice aurora and some streamers and so on, and of course you can see sort of typical Scottish cloud. So one thing that's always comes up when I talk to people about this is, well, how common are the aurora really? I know it's very popular to go off to Norway or Iceland to try to see the aurora, but actually, if you lived in, or if you live in somewhere like Lerwick up in the Shetland Islands, you'll typically see the aurora about once a month, actually. If you live further south, maybe down towards Northumberland, between, say, the north of Scotland and Northumberland, the north of England, you can actually see the aurora about once a year. And then if you live as far south as London, you'll see it about once a decade. But if you live in London, you probably won't because the lights are so bright. But the real reason you don't see the aurora is actually this stuff here, clouds. And really what happens is most of the time when the aurora happen, you can't see a thing. So that's kind of the reason why you don't see the aurora very often, mainly because of the cloud. It's a very cloudy place, the UK. So just some magnetic field words, just some terminology, just to kind of get you into the swing of things, so you know what I'm talking about. The Earth's main magnetic field is typically described as a vector. And at the moment, the vector in the UK points about 70 degrees into the ground and points approximately towards true north. When you measure the magnetic field vector, you break it down into its various components. Typically we talk about X or true north, true geographic north, Y is east or true geographic east, and then Z is downwards or towards the nadir or the centre of the Earth. And then the vector can be broken down into, you might be more familiar with these angles, declination angle, that's the difference between true north and magnetic north, and then I is inclination, dip into the ground. On top of that, something that I use in this talk is this idea H, which is this horizontal strength of the magnetic field in the magnetic north direction. So that is a fairly easy value to measure with a homemade magnetometer. And in fact, that's typically what your compass does. Your compass points along H because that's the strongest part of the magnetic field in the horizontal direction. Okay. There's been a long history of measuring the magnetic field in the UK, and in fact, Greenwich was one of the first observatories in the world to measure magnetic fields. That was one of their mainstays, along with obviously the astronomical observations they made. By the 1900s, the 1910s, the railway network around London had developed so much that it was interfering with the measurements. The trains using DC electric current were grounding just straight to the ground as they passed Greenwich. It was causing spikes in their data. So they moved to a place called Edinburgh, which is about 30 miles south of London, in Sussex somewhere. And at the time, they set up a state-of-the-art observatory. And it's got this lovely picture from the front of a magazine, true as the needle to the pole. And then if you read the little title down here, it says the veil has been rent away from the inner workings of an observatory. So back at those days, the simplest way to measure the magnetic field was essentially to hang a compass on a thread and then put a little mirror on that. And then they used sort of light levers to project a ray of light onto the mirror that would reflect back onto some photographic paper. The paper was on a rolling drum that would just slowly rotate over the course of a day and move. And so you get this trace, or magnetogram as it was called. Things didn't really very much change even up until the 1950s and 60s, where they still used essentially the same technology to do that. By the 70s and 80s, people were moving into electronic and digital kind of technology to make measurements of the magnetic field. And this is what a kind of current observatory looks like nowadays. They make absolute measurements of the magnetic field using a thing called a proton precession magnetometer. And that's about the size of a bottle of Coke, and it's filled with something that has a lot of hydrogen atoms in it, typically water or hydrocarbon. And they put a current around it, looped current around it, and they push all the atoms to be aligned along the magnetic field. They turn off the current, and the atoms start to precess. Protons start to precess, and then the precession of the protons is in phase for about a second or so, and the rate of precession is directly proportional to the strength of the magnetic field. So that measures the absolute strength, and then they measure the variation of the strength using things called fluxgate magnetometers, which is basically a little bar of ferrous material, like iron or something a bit more responsive to the magnetic field. Again, it's wrapped with a coil, and if you push a current back and forth to the coil, the current will balance out if there's no magnetic field. If there's a pre-existing magnetic field like that of the Earth's magnetic field, then it'll be easier to push the current in one direction compared to the other, and you can then relate that to the strength of the magnetic field. And they take 3 of these, and they point one towards magnetic north, one towards magnetic east, and one towards magnetic downwards essentially, and that gives you that 3 components of the Earth's magnetic field vector. So between these 2 instruments you can make absolute measurements of the field. Now, you need to be very careful because what you want to do is make long-term measurements. We're talking centuries here. So you want to make sure that your measurements are very clean, and so they put these instruments in sites that are typically in rural locations that are away from, you know, power lines and train lines and so on, and they make sure that the temperature is controlled and that there's very high quality calibration of the signal every week. So an instrument like that will cost you, you know, up to 15 or 20,000 pounds, and then to put it in an observatory and run it with staff will obviously cost you a lot more. So that's not really appropriate for a school. They wouldn't really want to field up 15 grand. So what I came up with was something that was not quite as accurate and a lot cheaper. So a Raspberry Pi is a computer. It's about £30. They're very popular at the moment in schools, and you can use them for programming. They're basically a little Linux computer. So what I did was I bought one of these, and then I attached a very cheap digitizer, which just takes an analog signal and turns it from, you know, a voltage, an analog voltage, into some numbers that the Raspberry Pi can read. And then I bought 3 relatively cheap fluxogate magnetometers from a German company, which were suitably accurate for measuring external field effects. So the problem with this system is that it's not temperature controlled. You know, you can put them anywhere, and they're very temperature sensitive. They're only good for magnetic fields from the ionosphere and the magnetosphere. They don't really do a very good job of measuring the core field. But they only cost about £150 all in, which is obviously 100 times less than an observatory system costs. And so it's about 100 times worse in terms of accuracy, but actually that's good enough for the kind of purposes that we're interested in. So I built an initial model with some funding from the Natural Environment Research Council, and that cost about £250 or so. So here's the kind of various bits I put together. So we've got the Raspberry Pis, the bit at the bottom. It's all green, sorry, it's not very interesting as such. These boxes never are very interesting, are they? It's more the kind of what you can do with them. The digitizer on top, and then it's got power supply and so on. And this cable runs to this magnetometer here, and it sits inside this Perspex, non-magnetic Perspex stand, and then there's 1, 2, 3 magnetometers for X, Y, Z essentially. Okay, and I put a thermometer on the bottom just to measure the ambient temperature. And then I put a glass, a sort of Perspex case on top, and that's really just to stop people poking it, because the first thing I noticed was people went, oh, that's really interesting, and start poking it. It's just people's natural instinct. So I did some tests. Edinburgh is here, as hopefully you know, and Estelmuir is one of the BGS observatories that we run, along with Lerwick and Heartland. And it's about 70 kilometres between Estelmuir and Edinburgh, which is not very far in geomagnetic terms. So I just ran the system for about a week or so in September 2014, after I built the initial system. And I happened to catch a geomagnetic storm around here, and let it run in the Edinburgh office. So the black line is the Estelmuir data, so that should be considered to be perfect. And then the blue line is the Raspberry Pi data coming from the office in Edinburgh. And it just shows the H value, so that's the strength in the horizontal component pointing towards magnetic north over the course of some days. And you see that I've captured a storm here, and then afterwards, as the magnetic field of the magnetosphere relaxes, it pulsates, called pulsations. And then every day, as the sun moves across the ionosphere on the daylit side, it depresses the magnetic field strength, and it creates this thing called the daily solar quiet current. So you can see that the 2 signals match reasonably well, in fact, better than I was expecting, except for there, where somebody came into the office and probably opened the door or something like that, and then closed it again, and that just created this offset for a few hours. So the system is very, 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 very sensitive. I had one set up in my house on a kind of shelf beside the curtains in the front room. Every time I opened the curtains, you could see me opening the curtains in the morning, and then in the evening you could see me closing the curtains as well. So very, very sensitive. But they are responding here. These differences are temperature response, temperature changes. So that inspired me to go get some further funding, and then I got around £10,000 from the STFC, which is the Science Technology Funding Council, and that allowed me to build 10 more systems and build a sort of more robust system, as well as a back-end website so that people could use the data from other schools. So the second system looks more or less like the first system, just a bit more better presented, and I put a little blue LED in the bottom of it, so it looked quite funky in the nighttime. And so essentially it's just the same thing. You get 3 of these fluxogate sensors, you plug them into this, analog to digital converter board. You plug that into the Raspberry Pi, and then you plug the Raspberry Pi into the internet, and you can send the data across the internet to the University of Lancaster's web server. Okay, so I went this time to test the system in Estelmuir. So here's again, blue is the Raspberry Pi, and black is the GDAS1 is the Estelmuir BGS system, and here's the horizontal field, which you can see matches very well over the course of about 5 days. Here's the vertical field, and you can see there's a difference arising here, but overall pretty good. And then just to show you why that difference arises, these red dots are the temperature variation in degrees multiplied by 10. So the temperature variation here is about 1 degree, 2 degrees, and then the differences between Estelmuir geomagnetic or BGS instrument in black and the horizontal or vertical fields in blue and blue and green are shown here. And you can see that as the temperature changes, so the error gets larger. So again, it's just due to the fact that the temperature changed very slowly over the course of 2 days. The BGS system is in a temperature-controlled environment. This other system was just left in a kind of basically a shed, so it wasn't particularly well controlled. And during October, obviously this is quite a warm day, surprisingly, compared to the rest of the days. So that showed me that the system was very good at detecting small-scale changes as long as you kept it temperature-controlled. So then I went out and I went to a load of schools. I went to various Institute of Physics teachers' meetings and so on, and I managed to get 10 schools around the country to agree to take these systems on long-term loan for around about 2 years. So the blue is where I deployed them all in the end, black is the BGS observatories, and then these sort of red ones are the University of Lancaster's variometer systems or magnetometer systems that they run separately. So you might think it's a glamorous job. Here's the cupboard in Benbecula where I set it up. Here's the back of the classroom in Alexandria, and here's the back of the other classroom in Norwich. So, you know, I got to see a lot of very exciting cupboards and backs of classrooms. So what does the data look like? Well, you just basically, as far as the teacher is concerned, just plug it into the network, set up the Wi-Fi or put it into the Ethernet, and then turn the system on, and then it starts logging automatically. And it sends the data back to the University of Lancaster's Aurora Watch UK website. And some of you might have the app on your phone, which gives you alerts if there's going to be a predicted large-scale aurora, or if the magnetic field starts changing suddenly. So if you go to this website, you can see these plots. Again, here's the traces from each of the flux gates, the horizontal flux gate, that's one pointing magnetic north, magnetic east, and magnetic down. And you know, when the school is quiet, typically at weekends or summer holidays, then you can see that the traces are very, very good. When the school is not so quiet, you get these kind of random steps of the data. Some schools are really good, some schools are terrible, but that's just the way it is. But overall, the data was surprisingly good, and I was quite pleased with how it came about. So just to show you an application of this, it wasn't just to teach children about the magnetic field, it was also actually a sort of slightly selfish reason. I wanted to gather some data about the variation of the magnetic field across the UK during large geomagnetic storms. And that opportunity came on the 7th of 8th of September, 2 years ago now, or 18 months ago now, when there was the largest solar storm of this present cycle, 24. So here's some nice pictures I found on the internet. Here is the Tay Bridge in Dundee and the Aurora over there. And I don't know if you might be able to spot, here is the Forth Road Bridge and Forth Rail Bridges just on the other side of Edinburgh. And again, you can see the Aurora just across the top there. It's not very particularly bright. I went away and I gathered the magnetograms, so this is the magnetic field information, not just from my magnetometers in the schools, but also from a host of magnetometers around the North Sea. So, and then I stacked the traces running from kind of geomagnetic north to geomagnetic south. Dumbash is a geomagnetic observatory in Norway. Lerwick is in the Shetlands. Here's BGS7, that was in Glasgow. Here's Estelmuir. These ones are the ones around East Anglia and Peterborough. And then Valentia is on the west coast of Ireland. And then Doubre is an observatory in Belgium. So you can see that this is a trace of this horizontal strength of the field, and on this particular storm, the shock arrived around midnight on the 8th of September. You see a sudden depression in these high latitude observatories, which sort of decreases as you go north, and actually it's in the opposite direction by the time you reach Doubre, so that's essentially a line current, and you're seeing it from different directions, different locations. And then it was quiet again for a few hours, and then the storm kicked off again here later on in the middle of the 8th of September. So those look nice on their own, but what you can do is something better. You can put them into a map, and you can look at how the aurora essentially has structured during the course of the storm. So that's what I did. I took all this data, and I used the traces to turn them into a map of how the variation of the magnetic field, or how the magnetic field varied during this storm. So just this is in the north pointing direction. This is in the east pointing direction. I'm going to start around 10:30 and just run it quickly for a few hours. Don't worry, it's not in real time. It'll speed it up. And hopefully you'll see that in this direction, you'll see basically the aurora kind of electric current coming down here and sort of running across the UK, and it moves back and forward. And then in the east component, you can see it moving back east and west as I run the movie. So here we go. Here's this aurora line moving back and forward. So this is the aurora passing over around midnight, and that's when those pictures were taken as showed in the previous slide. And then as the storm decayed, the aurora moves back further north again. Okay, and then just restart the movie again. You see it go back and forward. Okay, so that is interesting information, and all these white circles show the dots that I used to create these maps. And again, some of these were the BGS magnetometers collecting data from the schools, and particularly these two here in Undle and Norwich, because actually they were the ones that had been up and running quite well for that particular storm. So the whole point about the project was to get schools to understand a bit more about the Earth's magnetic field, and also then to gather some data for myself for use in my research. And then just to kind of touch upon what that research is, it's related to what's kind of commonly called space weather. So this is the effect, particularly from my point of view, of the sun's magnetic field, or the interaction of the sun and the Earth's magnetic field, and the effects directly on technology. And one of the things we look at is the effect of so-called geomagnetically induced currents on the power grid, and having information about how the magnetic field varies in detail across the UK is very important for that. Previously, we just had Lerwick, Estelmere and Hartland, which would just basically give us a line and just show us where sort of roughly the aurora were moving back and forward during the course of a geomagnetic storm. But with all these additional magnetometers and variometers, we now have a much more detailed and nuanced understanding of how the magnetic field changes. And that turns out to be actually quite important, because locally you can get very sharp sudden enhancements that create dangerous geomagnetically induced currents, which can damage transformers and so on within the power grid. Okay, so I'll just leave it there. Just want to say thank you, and just acknowledge the funding from public engagement and all the people who helped on the project. So thank you.
Thank you very much indeed. So the paper's open for questions or comments. Yes, Horace.
It's actually a very brief comment. It is a wonderfully brilliant project, bringing science to children and children to science. And I hope the principal people involved can be awarded a prize for it.
Other questions? Yes, Simon.
Thank you. I've got a history of science comment, which is in 1692. Edmund Halley published a paper in the Philosophical Transactions about the magnetic variations in the north and south of the Atlantic, and he did some modelling from that. A striking feature of the paper is right towards the end. He says that he hopes master mariners will follow his instructions for measuring magnetic variation at sea, and that they will send their observations into the Royal Society when they return from their voyages. I don't think that ever happened, but as far as I can tell, it was the first attempt to set up a magnetometer network.
Yeah, very good. Yeah, a lot of those measurements were collected by Andy Jackson in his 2000 paper, looking at the historical magnetic field. So yeah, somebody else had to do the work.
Other questions or comments? Yes, please, in the middle here.
Thanks. Is the current pole wandering? I know it doesn't make a lot of difference in terms of our variation here at the moment, but is that causing any significant changes in the aurora that's happening?
Yeah, it's a good question. So yeah, the pole has been moving very rapidly over the last 20 years or so, and it's moved from kind of northern Canada across towards Siberia. Yes, that will have an effect on the location of the aurora. At the moment, I think it's sort of dragging it sort of towards Russia, away from, say, northern Canada and North America. But it's not really dragging it towards us, if that's the kind of...
Is it changing the magnitude as well, or is it just where it's happening?
I'd have to refer you to the literature for that one. There's been a paper out recently about it, and one of my students did actually write a paper about this a couple of years ago. I think we don't know if it's changing the magnitude. It's definitely changing the position. As to whether it's changing the magnitude, that's harder to say, really. We don't really have long enough records from, say, satellite to make a good estimate of that.
So last question now.
Well, my question is that, it was quite interesting to see the graph of the temperature and also all the magnetic fields, but what it is interesting to know is whether the temperature variation has effect on the magnetic field, and if it is so, what is the effect on it, so that kind of whether it's applicable to certain areas in the commercial field,
Yeah, so the temperature effect is actually on the sensor. So the sensors are, because they're quite small, the temperature changes then, it's made of metal, so they lengthen or shorten, and that changes their response to the magnetic field and changes the calibration. So you can sort of account for that if you've measured it, which a lot of people do, try and calibrate that out, but it's not perfect. So, and it also varies between different sensors, so you have to do it for all of them individually.
But, sorry, just one more, is that, there's a lot of, gossips going around is that the magnetic field in this planet is getting weaker. And I do not know whether scientifically if it is true or not. If it is true, then is the shift of the Earth is going on the other side, is changing and has changed quite a bit considerably. Is it related to because this Earth planet is getting warmer day by day, year by year?
Well, there's nothing to do with climate change, actually. Because the main field comes from the core, so that's completely isolated from the surface of the Earth. So the field is weakening, but if you look historically at, say, the last 10,000 years, it just varies with strength. It goes up and down. So actually, at the moment, it's sort of on average for the last 10,000 years. The last 3,000 years has been stronger. Prior to that, it was a bit weaker. So the strength itself varies, and the position of the actual magnetic pole changes all the time. But there's no reason to think we're going to a reversal, actually, if that's the kind of question. And no, there's no link between the surface temperature and the outer core. The outer core is at 3,000 degrees, so it doesn't really matter if the Earth's surface varies by 1 or 2 degrees as far as it's concerned.
Okay, let's thank Dr. Beggan again. Thank you.